All right, welcome to projectile motion, which is the combination of an object experiencing free fall and also moving at a constant speed at the exact same time. All right, if you've ever played Angry Birds, the rationale between changing the angle and increasing the pull of the bird, that's all projectile motion. So let's review free fall because all of these free fall rules come in very handy for projectile motion. All right, so keep in mind that when an object is falling or moving downwards, acceleration is positive. All right, and if the object is, say, in an upwards portion, then the acceleration is negative. The reason for this is because gravity is always pulling you down. So if you're trying to go up, gravity works against you. But if you're trying to pull down, gravity works with you. Okay, because gravity is always down. Another rule to remember is that with free fall, the vertical speed at the top, at the very, very, very top, is always 0. All right. Another thing to remember, if an object leaves your hand with a certain speed, right, so say 5 meters per second, and it comes back to your hand at the exact same height, returns to the hand with the exact same speed, 5 meters per second. All right. Same thing, time it takes to go up is equal to the time it takes to fall back down. All right. Learn these, know these, be familiar with them. Just keep in mind, this is all for vertical. We'll get into more detail with that, but all for vertical. So projectile motion involves a combination of vertical and horizontal motion. All right. One thing I want to state right now is you must separate the two because they follow different rules. All right, because things that are moving vertically versus horizontally, which one actually has gravity involved? Think about it, which way does gravity point? Gravity points down, that would be a vertical direction. So vertical motion is affected by gravity. The horizontal motion, however, is not. All the horizontal motion is constant speed. All right. Another way to think about this is that vertical uses our acceleration equations. So v equals VO plus AT, or x equals XO plus VOT plus 1/2 AT squared, or v squared equals VO squared plus 2a x minus XO. All right. So vertical uses all equations that involve gravity or have acceleration in them. Horizontal, however, is constant speed. So the only equation you'll be using with horizontal is that velocity is equal to distance divided by time. All right. Keep them separate. This will make more sense as we get into some problems. But some rules for projectile motion, very, very important rules to always obey. When you start defying these rules, things start going wrong. All right, so motions in horizontal and vertical are independent of each other. All right, we cannot combine them together. You can't use the velocity equals distance times time velocity equals distance divided by time with your vertical component. Doesn't work. And you can't use an acceleration equation with your horizontal component. All right, you have to keep horizontal and vertical completely separate. All right, another thing to remember, your velocity in the horizontal direction is constant. It will never change. It will always be the same velocity because acceleration does not affect the horizontal component. However, velocity in the vertical direction, it will change. Will change. And it does because it's experiencing gravity, which is an acceleration. All right, so depending on the direction of the projectile's motion. If it's going up, gravity will slow it down. If it's coming down, gravity will speed it up. That does say will change. All right? And then the key important thing, the only thing that ties the horizontal and vertical together is time. All right? And the reason for this is we have a constant speed in horizontal, which means that object could keep moving forever. But the vertical component eventually reach the ground. All right? So once the vertical component hits the ground, the horizontal component stops. Which means time for both is the same. It's just another way of saying what I wrote there. All right? Once the vertical component has completed its trip and we've come back to the ground, horizontal component has to stop because it can't keep going. It's hit the ground. Okay? So let's look at a couple of examples. There are two major types of projectile motion problems. There is straight, and I'm going to add in the word horizontally straight off of an object. All right, these are usually cliff problems. All right, what this means is that your starting vector or even your starting velocity is all horizontal. So, if this black ball is shooting off at 5 meters per second, the Vx is 5 meters per second, or your horizontal x, 5 meters per second. Now, time, it always comes from the free fall component because that's what actually ends at some point. All right, so in this case, your time is dependent on your height. All right, the higher up you are, the more time it'll take to reach the ground, so therefore the more time the ball will spend in the air. All right, so height determines how long the ball will be in the air because that determines how long the ball can fall. All right, which means your distance horizontal, which would be here, so let's make this blue. Your distance horizontal is going to be dependent on that time that you'll have to calculate from the free fall portion and your starting velocity. All right. One thing to add in here, since all of the velocity is horizontal, your y component for these problems is always starts out as 0. All right, which according to free fall, as it falls, the y component will increase, but it starts out at 0 because up until the point where the ball leaves the cliff, we're not falling. All right, just some rules to keep in mind for this. So here's an example. Projectile motion straight off a cliff. So we have a ball that we throw horizontally with a speed of 12 meters per second off of a cliff with a height of 45 meters. So let's label some things. We know this is 45 meters high. We know that our velocity is 12 meters per second. Good thing to do in these is to split velocities up into Vx, which is horizontal, and Vy. So our Vx is 12 meters per second, and at the top, Vy is 0. All right. So it says, how far away from the bottom of the cliff does the ball land? So our big question is that distance. All right. Projectile motion problems inherently end up being multi-step. So what we need to do is first find the one thing that ties vertical to horizontal, and that's time. All right, so since we have an initial velocity for the vertical, we have a height for the vertical, we can find time. So we're going to use this equation. X equals VOT, It's 1/2 AT squared. Now, our VO in the vertical, all right, if you see A in an equation, you better be working with a vertical velocity, is 0, which means this component doesn't matter. So really, our height, 45 meters, is equal to 1/2. Since we're falling, it's positive 9.8 times t squared, which ends up being, t is the square root of 2 times 45 divided by 9.8, which calculates out to be 3.03 seconds. All right, so now we have our vertical figured out. Now we need to find our horizontal, which means we can use our horizontal speed. And the only equation that helps us with horizontal things is v equals d over t. We now know that our speed is 12. Distance is unknown, but it's going to take 3.03 seconds, which means our distance is equal to 12 times 3.03, or 36.36 meters. All right? This isn't everything I could possibly ask you, but if you stay organized, if you make sure that you keep your x component separate from your y component, you only use the acceleration equations with a y component, you only use v equals d over t with the x component, you can answer just about anything. Okay? So the second major type of problem is arcs. All right? With arc problems, we have an angle, a theta, that determines the starting vertical and horizontal velocities. All right? So theta determines this. So in order to help you find, we've dealt with breaking things into components before, I just want to redraw these vectors so that you can see the bow tie. So your vertical would be like this, your horizontal would be like this, your theta is inside the triangle. So in order to find your horizontal component, it's cosine theta. In order to find your vertical component, it's sine theta. Okay? Once again, vertical component determines how long the object is in the air, because the vertical component obeys rules of free fall, and free fall is the only thing that can actually end. Constant speed won't end. All right? Then, once again, your horizontal component will determine how far away the ball lands in the horizontal direction. Okay? So just a couple of other things to keep in mind on here. At the very top, based on free fall rules, your y component is going to be 0. All right? If you notice, all of the blue arrows are the same length, which means your v sub x is the same number the whole time. All right? Because remember, one of our projectile motion rules is that horizontal velocity does not change. Vertical velocity, however, is going to go from a higher number to 0 back to a higher number, following free fall rules. So let's use this for a problem. So, football is a great time to see projectile motion with an angle. Here we have a kicker punts a football down the field. The kick has an initial velocity of 12 meters per second, 37 degrees above the horizontal. How far down the field will the ball hit the ground? So, our angle is 37 degrees. All right. Now, and the initial velocity, let's scoot this over so we have some room to see it, is 12 meters per second squared. When you have an angle, that 12 meters per second squared, never use it. It doesn't help. It's combined horizontal and vertical. All right? We can't use v equals distance divided by time and an equation with acceleration at the exact same time. It's not possible. All right? So that means that the 12 meters per second, it's not possible for you to use an equation, not in this classroom, okay? So whenever you see an angle, your immediate reaction should be, I need to break this up into components. So Vy is going to be 12 sine 37 degrees, which is equal to 7.22 meters per second. Vx is equal to 12 cosine 37 degrees, which is equal to 9.58 meters per second. All right, now that we have our separate vertical and horizontal velocities, we can do much of the same things we were doing before. All right, we just need to keep in mind that in this situation, we are going up, so slowing down, and then also going back down, so speeding up. So, good thing to do, again, we need to find time, split it in half, because this gives us a known other velocity. So up here, Vy equals 0. So if you think about our initial velocity down here being 7.22, or over here, Vy would also be 7.22. All right, you can use this equation, V equals Vo plus At, to find your time. So I'm just going to use the first half. So we'll have 0. We'll have 0 equals, oops, sorry. Hit a button and lost my train of thought. 7.22 plus 9.8 times t. Or, and sorry, we are going up, so that's a negative 9.8. So we'll have negative 7.22 equals negative 9.8t, and t is equal to negative 7.22 divided by negative 9.8, which is equal to 0.74 seconds. Now, if I wanted to say know that highest height, this would be the time to use. But I am going to ask for the total horizontal distance in this problem, which means we need to, so far we know that this time is 0.74, but same thing for this half, 0.74. So we need to multiply that by 2. So our total time is t equals 1.48 seconds. So now that we have time, let's switch to our horizontal information and find the total distance traveled. So that's going to use that velocity and the one thing that ties the two together, time. V equals distance over time. All right, so 9.58 is equal to distance divided by 1.48, or distance equals 9.58 times 1.48, which is equal to 17.76 meters. All right. Again, the trick to this is just making sure that vertical is separate from horizontal. Vertical is the only velocity you ever use acceleration with. Horizontal, you only use v equals d divided by t with it. And never, ever, 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 ever use the angled velocity.